This is going to be another video of mixed bag problems when we are trying to factor polynomials. And in this case, the polynomials can be of any degree that we have learned, and that could involve multiple variables as well. So we're going to go in order and try to see what are the features we want to go through for factoring. And again, just like any factoring problem that we have done before, always make sure you check GCF first. I sometimes have to remind myself to do this as well because it's really easy to overlook, even though it oftentimes makes our calculation or next process much easier with smaller numbers. So always do that first whenever you are going through the factoring process. And starting from part A, we have this linear expression, and when we have this case, we want to check GCF first, and we do have a GCF between the two terms. We can factor out -3 as a GCF, and that leaves me with y in the first part and +1 in the second part. And remember, you can always check your factoring by redistributing or FOIL later on to check whether you get back the original expression. And once we have done this, we recognize -3 is -3, y plus 1 cannot be factored any further, so we're done. Moving on to part B, we have a higher degree polynomial, and especially with this case, we always want to make sure whether there are any GCF we can take out. And in this case, there are two parts we want to consider. First, for the constants, we have 30, 12, and 42. And you might want to refer back to the video on how to factor GCF first to remind yourself how to find the constant GCF if these numbers are large. But if you recognize it right away, we will see all three factors, the coefficients part, contain a factor of 6. 30 is 6 times 5, 12 is 6 times 2, and 42 is 6 times 7. And here, for the variable part, we always want to take out the lowest degree of the variable. So the lowest degree of the variable across the board is r squared. So we take that out as GCF. Once we do so, from the first term, I'm left with 5r squared. From the second term, minus 2r. Third term, plus 7 over here. And once we have this form, we want to again check whatever is in the parentheses, whether it can be factored further. And in this case, it can, because we have a quadratic expression still. And when the leading coefficient is not equal to 1, we have to try the AC method. And I believe in this case, AC method works out over here. So for the AC method, we want the product to be equal to 5 times 7, which is 8 times c, 35, and we want the sum to be equal to -2. If you go through the factor pairs of 35 over here, you will get the result that unfortunately it doesn't work. I thought it was very close because I was thinking about 7 and -5 or 5 and -7, but in this case we want a product of +35, so it actually doesn't work. So we can't really do AC method, and that leaves us with the result that we can't factor this any further. And we could, if we were looking for x-intercept, we could use quadratic formula, but in terms of the factorization with only integers, there is no such numbers or no such integers that satisfies these conditions, and therefore the resultant expression in the parentheses is actually prime. We can't factor that any further. So that's actually as far as we need to go for this problem. I guess in a way that's lucky for us. We don't have to go all the way to find x-intercepts. And now moving on to part C, we want to again check GCF. Here we have a constant of 8 and a variable of y that we can factor out. And then once we do so, the first term is left with just x, and second term, it just keeps itself, +1. Never forget the +1, it's important to hold the place. So we start with 2 terms, and we still end up with 2 terms in the factored form over here in the parentheses. And that's as far as we can go because we can't factor x plus 1 any further. Moving on to part D, we have again a case of 4 terms. Whenever that happens, factor by grouping is our go-to method. So first two go together, last two go together, connect by plus. And from the first parentheses, the GCF is t, so I'm going to go ahead and factor that out, leaving me with t minus 2. From the second parentheses, I have a factor of positive 3, so I'm leaving positive 3, and that leaves me t minus 2 again. So altogether, I can take out t minus 2 as a common factor between two groups, and t plus 3 from the leftover part of our groups. And that's going to be the fully factored form that we have. Now moving on to part E. As usual, feel free to take some time to pause the video, take notes, digest all the information before you move on. So only move on when you're ready to the next problem. And for part E, whenever we have, again, this form, we have 4 different terms, so we want to consider the factor by grouping again. And here, if I group the first two together, last two together, this is a case we have 2 variables, but the process idea is still identical. We want to think about whether there's anything that's in common. And in the first group, we see x cubed minus 3. We can't really do much about it. And in the second group, we have 2x cubed y minus 6y. A common factor of 2 pops up. Variable-wise, we have y in common between the 2 terms in the second group. And that leaves me with x cubed minus 3 again. Great, and once we have this form, recognize that x cubed minus 3 is really 1 times that. So if you see that, we can factor x cubed minus 3 out from both groups, leaving us 1 plus 2y over here. And we can't further factor either factor anymore, so we're done factoring with this problem. Part F, that's actually the one I was thinking of when I was looking at the part B for possible further factoring. In this case, we can actually use the AC method over here. So if I use the AC method, I want my product to be negative 35. Great, and sum to be equal to negative 2. And we will find 2 numbers that would actually work, which are negative 7 and 5. Meaning I'm going to rewrite this expression to be 5y squared minus 7y plus 5y. And then minus 7. And once we have 4 terms, factor by grouping it is. From the first group, we have y in common, so we get 5y minus 7. From second group, nothing common, so we just write it as 5y minus 7. If you want to, you can write it as 1 times that. You don't have to, but it's just a nice reminder that you need this placeholder over here. And then 5y minus 7 in common, y plus 1 left over. We can't further factor either expression anymore, so this is all done. That's as far as we can go for factoring. Moving on to part G, I have this expression in part G, which again, leading coefficient is not 1. That leaves me the possibility that I have to use the AC method. If I can't use AC method to find the integer answers, that means I can't factor any further. And here, if I go ahead and do the AC method, that indicates that the product of the 2 numbers I need is 2 times 5, which is equal to 10, and the sum of the 2 numbers will be negative 6. And we know the factors of 10 are 2 and 5, and 1 and 10, and the negative parts of that. In this case, I don't think any of the numbers would work, so this is a case where this is a prime polynomial. That means we cannot factor any further, because there are no such integers. That works for the AC method. Lastly, we have this, again, trinomial, and we want to check whether there's any factor that would work out for our process. And here we want to check AC method again because there's no GCF to be taken out first. The product over here will be 8 times 15, which is 120, and the sum is 22. And great, this time it actually works. The two numbers we can find. Feel free to take your time to look for it instead of continuing the video. We have 12 and 10. That would actually work. Therefore, we get 8t squared plus 12t plus 10t plus 15. Sorry, yep, plus 15, that's right. And once we do so, factor by grouping, it is the first group we have 4 and t in common. Once you factor that out, you're left with 2t times 3. Second group we have 5 in common. Again, you should be left with 2t plus 3 in common. And altogether, we would have 2t plus 3 times 4t plus 5 as a result. And that's going to be as far as we can go for factoring these problems.